4, properties of exponents and radicals, is going to continue to see our development in the relationship between the two. So in this opening exercise, they're going to say they want us to write each exponential expression as a radical expression. So even though we may not need it to solve it, they want us to do that, and then use a definition and properties to write the results as an integer. So if we did that, right, that means 7 1/2 would be the same thing as the square root of 7, and then another 7 to 1/2 power would be another square root of 7. So now that we both have radicals, 7 times 7 is 49, so now we have the square root of 49, and that results in us getting a 7. So in letter B, they want us to do the same thing. So we write the cube root of 3 times the cube root of 3 times the cube root of 3. And so when we do that, 1, 2, 3, that would be 27. So the cube root of 27, and then again we happen to get a 3. That's not going to happen every time, but that's been the pattern. So here we get the square root of 12 times the square root of 3. And so we multiply it together, we get the square root of 36, and then our result is 6. Here we have a different kind of thing going on, so we'll take a look at each one separately. That means we are going to take the cube root of 64, and then after we do that, we're going to take the square root of that. So the cube root of 64 is 4, and then the square root of 4 is 2. So again, remember that the goal of that exercise was for us to rewrite each exponential as a radical expression in that design. So when we look at examples 1, 2, and 3, they say write each expression in the form of b over m over n, and so a rational expression, for positive real numbers b and integers m and n, such that n is greater than 0, by applying the properties of radicals and the definition of the nth root. So again, while we may not need the radicals, they want us to use the radicals in this design. So if we did that, that means we would write this as a 4th root of b times a 4th root of b. That allows us to multiply these. So now we get the 4th root of b squared. So now that we applied our properties of radicals, we can now rewrite this as b to the 2/4 power, which reduces to b to the 1/2 power in that design. Now again, let's make sure we're clear. I understand that if you're watching this video, you might say, Miss Daycourt, if they got b to the 1/4 times b to the 1/4, all I have to do is add the 1s to get b to the 2/4 and then simplify. Yes, I understand that. All I'm doing here is I am applying the property of radicals per the directions. This is all I'm doing when I wrote that in blue. So same thing here. If I'm applying the properties of radicals, this would be the cube root of b, and then we would have the cube root of b to the 4th power, which means when I multiply the insides, I add the exponents. So I end up with b to the 5th power, because 1 plus 4 is 5. And then we would end up rewriting this as b to the 5/3 power. Right? That's if I'm applying the properties of radicals as requested by the directions. So here, same idea in this principle. If we take a look at it, we've got a 5th root and a 4th root. So what we're going to need to do first is we're going to need to be able to create common denominators. So I'm not going to be able to apply radical rules if I don't have the same radical. So this is what I currently have, and we're going to create common denominators. So our common denominator is going to be a 20. So multiply top and bottom by 4, so you get b to the 4 over 20. And then you multiply this one by 5, And so you get b to the 15 over 20. Now, once I've accomplished that, let's make that look like a 5, because it really looks like a 3. Now, once I've done that, I can rewrite this as radicals. The 20th root of b to the 4th power, and then the 20th root of b to the 15th power. That means I can add these, so I get the 20th root of b to the 19th power, and then I can rewrite that as b to the 19th over 20th power. So in exercises 1 through 4, they say write each expression in rational form. If the numeric expression is a rational number, then write your answer without exponents. Here in this exercise, they do not give us the stipulation that we have to use radicals. So we're just going to simplify to the appropriate way that we can. So we take a look at this, and we notice we have b to the 2/3, and we have b to the 1/2. Well, I can't add these fractions because they don't have common denominators. My LCD is going to be 6, so I multiply this one by 2. So I end up with b to the 4/6. And this one I multiply by 3, so I'm going to end up with a 3/6. And when I add my fractions, 3 plus 4 is 7, I get b to the 7/6. Here we have a power raised to a power. Remember, if you have a power raised to a power, you're just going to multiply everything. So here we're going to just multiply -1/5 times 2/3. And so it's going to be b to the -2, because -1 times 2 is 2, and 5 times 3 is 15. I do not have to have common denominators for a power raised to a power, so that is unnecessary. Here we've got another case where we've got 64. I have a typo on mine. Let me verify that your book matches, because I believe it's supposed to be a pair of 64s. And let's see, this is on page 29. Yes, these should be a pair of 64s. Let's see if it's going to let me change that. It might not. It might. Yeah, there we go. So now that's correct. So this one's going to work like number 1. So instead of b's, we have actual numbers, so we can actually simplify this one. But again, you can see that we don't have common denominators. So we do have to deal with and address that first. So we end up with 64 with a 1/3. And we have a 64 with a 3/2. We're going to multiply this one by 2. So we're going to get 64 to the 2/6, and then we're going to get 64 to the, if we multiply these by 3, be 9/6. That means when I simplify this, I'm going to get 64 to the 11/6 power. The 11/6 powers. So we can simplify this one, right? We could rewrite this one as 6th root of 64, and we could raise that to the 11th power. So it turns out the 6th root of 64 is 2, and then 2 to the 11th power, and it's okay to pick up a calculator for these. Don't feel bad about that. You get 2,048. So same idea happens with number 4. We have a power raised to a power with a fraction. So we can multiply this 3/2 to the 3 and to the 2. So when we do that, we get 9 and 9/2. And then we get 4 and 6/2. In that one. So now once we accomplish and deal with that, we can start to simplify. So for example, it might be worth writing this one as the square root of 9 to the 9th power. and this will be the square root of 4 to the 6th power. Well, we know the square root of 9, that is 3, so you end up with 3 to the 9th power, and you end up with 2 to the 6th power. So 3 to the 9th power ends up being, and again, you pick up a calculator for that. That ends up being 19,683, and then 2 to the 6th power is 64. And that ends up being your final answer in that exercise. So next they say in example 4, they want us to rewrite this radical expression so that there are no perfect square factors remaining inside the radical. So they want us to simplify this piece. So we're going to drag this down here, make it a little bit larger to look at, and address it. So, for example, something that goes into 48. That would be a 16 times 3. Let's make sure that's right. 16 times 3 is 48. Now, this is a square root, so that means we want all of our exponents as possible to be even. So when we do that, this x to the 5th, we're going to rewrite this as x to the 4th times x to the 1st power, because 4 plus 1 is 5. My y to the 4th is already even, and my z squared is already even. So now what we're going to do is we're going to take all the perfect squares out. The square root of 16 is a 4. The 3 we leave alone. The square root of x to the 4th, or in other words, 4 divided by 2, is x squared. Can't do anything with this one because it's odd. This is another y to the 4th, so it becomes y squared. And then 2 divided by 2 is z. So that goes on the outside. Left over on the inside is a 3 and an x. So in exercise 5, they want us to do the same. And then they say in the exercises here, which we're not going to do for the exercise purposes, if the problem set does ask for it, then that's fine. It says then evaluate the resulting expression for these values. We're just going to focus in this exercise of simplifying these radicals. So when we look at this idea, we take a look, the square root of 8, we can break this into a 4 and a 2. Because this 3 is odd, we're going to break this into an x squared times an x to the 1st power. And the y is already squared, so we leave it alone. So now we take all of our perfect squares. The square root of 4 is a 2. The exponent, 2 divided by 2, is 1. And then y squared is going to give us a y on the outside because 2 divided by 2 is 1. And so what gets left on the inside? That remaining 2, this one right here, we'll highlight it. This remains on the inside, and this one remains on the inside of the radical. And then that ends up being the end of that problem. They say rewrite each expression as rational exponents containing as few fractions as possible. So if we did that, it would just be rewritten like this, and it would be times with a 2x on the inside of the parentheses raised to the 1/2 power. And the only thing to that is the author is reminding you that you can rewrite it as an exponent or you can rewrite it as a radical. It doesn't really matter. So here, the 54, let's see. We need to think of something that's a 54, maybe a 9 and a 6. So remember, this is a cube root. So we're trying to think of something that multiplies to give us a 54. I think it's a 27. 54 divided by 27. Yeah. So 27 times 2 times 2. Now, because it's a cube root, we have to get something that is divisible by 3. So we're going to rewrite this as y with a 6 and a y with a 1. There's nothing we can do with the z squared that's going to make that work. We're going to separate this a little bit. I don't think it's going to let me grab it. Nope. So anyway, the cube root of 27 is 3. 6 divided by 3 is y squared. And everything else has to stay on the inside. So the 2 stays in there, the y stays in there, and the z squared stays in there. And so that would be the radical version of that. If we wanted to change this to a rational exponent containing as few fractions as possible, that would become 3y squared would stay there. And then this would be 2 to the 1/3 power. And then this would be y to the 1/3 power. And then you would have z to the 2/3 power. In that perspective. And so let's see. What else? That would probably be as far as I would consider taking it. In that perspective, I'm sure I could go a little bit further, but again, it's not necessary. All right, so that'll be the end of this section. We're going to skip exercise 6, and then that'll just take you to the problem set, which is not that. So you want to disregard that. That was from another year. And so that'll end lesson 4.